So not all functions can be annihilated. So there are other methods for solving this. And in fact, some people say, why don't we just do the variation parameter method because it works beautifully. But it can be kind of nasty to do sometimes. So it depends, and it's nice to have multiple ways of doing things. We're going to go ahead and let's just look at a second order differential equation. It is a little bit harder to do higher orders, but we'll do the second order one. We're going to solve this similar to how we solved the first order differential equation. Standard form is always going to be y sub double prime plus p of x y prime plus q of x y equals f of x. In other words, there's a 1 in front of the y double prime. And that was something we did when we solved first order differential equations. We got rid of the function in front of the y, the highest order derivative. We are going to assume that p of x, q of x, and f of x are all continuous. Otherwise, then we have some problems. So we're going to go this, we're going to solve y double prime plus p of x y prime plus q of x y equals f of x. We're going to assume that y sub p is y1, u1 times y1 plus u2 times y2. Y1 and y2 are solutions to the homogeneous equation. So it always goes back to that associated homogeneous equation, find out what those are. And then once we know what those are, you'll see that the solutions are just multiples of those, some function multiple of those. Your y sub p prime would therefore be u1 prime times y1 plus u1 times y1 prime plus u2 prime times y2 plus u2 times y2 prime. And your second order, of course, same thing. You've got product rows going on here, and that's all we're doing is doing the product row a bunch of times. Seed of y double prime, u y double prime times y1 plus u prime, u1 prime times y1 prime plus u1 prime times y1 prime plus u1 times y1 double prime. And the same thing with u2 double prime times y2 plus 2u1 u2 prime y2 prime, and the 2 came from because there's going to be 2 of them like there was on the other one, and plus u2 times y2 double prime. And that will always be the case whenever we're assuming that y sub p is u1 times y1 plus u2 times y2. So you won't ever have to find these again. They're always going to be the same. So we've got, remember, if this is a solution, it will satisfy the different equations. So we can plug in the y sub p double prime plus p of x times y sub p prime plus q of x times y sub p equals f of x. So we plug all those in that we had before. And then we're going to go ahead and realize that some of these terms have a u1, some of these terms have a u2, some of these terms have a u1 double prime, some have a u1, some have a u2 double prime, some have a u2. So we're going to go ahead and put all of our terms together. The ones that have a u1 has y1 double prime plus p of x times y1 prime plus q of x times y1 plus u2 times y2 double prime plus p of x y2 prime plus q of x times y2 plus there's a u1 double prime times y1, there's a u1 prime times y1 prime, there's a u2 double prime times y2, and a u2 prime times y2 prime, plus a y1 prime times u1 prime, plus a y2 prime times u2 prime, plus a p of x times u1 prime, y1 prime, plus u2 prime, y2 prime. Notice you had that p of x times all that equals f of x. So we collected all of our terms together. We came up with all this values happening. And the really cool thing is that the derivative of u1 times y1 is the u1 double prime times y1 plus u1 prime times y1 prime. That is that derivative. It's just the product rule. And the derivative of u2 prime times y2 is u2 double prime times y2 plus u2 prime times y2 prime. Again, that's just the product rule. So these terms all come out really nicely here for us. And we can see that this derivative here are these first two terms right here, and this second derivative, the derivative of u2 prime y2 is the terms u2 double prime y2 plus u2 prime y2 prime. The p of x, we don't have to change that, so we've got plus p of x times u1 y1 plus u2 prime y2 plus u2 u1 prime plus y1 prime plus u2 prime times y2 prime equals f of x. So we have all this. Okay, it's all coming together. We can all see things happening and what's going on. I'm collecting all of our terms together. We now see we have a derivative. This is just the derivative of each individual term. So we can actually think of it as putting these derivatives together. The derivative of sum is the sum of the derivatives. So we can put those together, and then we've got the rest of this going on. Okay, so all this is happening. This looks like a lot of algebra. That's a lot of what it is. We're going to let u1 y1, u1 prime y1 plus u2 prime y2 equals 0. Okay. Cramer's rule, and we're going to let y1 prime u1 prime plus y2 prime u2 prime equal f of x. So we're going to just let that happen. I do want to go back and just mention one other thing. You notice the q of x's are gone. And that is because u1 prime y1 prime plus u2 prime y2, I say u1 times y1 plus u2 times y2, those actually will go to 0. So this is why the q of x's all went away, is all that went to 0. And so that's why all that kind of happened for us, is it all went to 0 and those terms went away. So that's why those all go away and what happened with those. So again, what we're doing here with this is we're letting, if we think about what we have here, is we've got basically a y1 prime u1, a y2 prime u2 equals, and then we got this y1 prime u1 prime u1 plus y2 prime times u2 times p of x, and then the rest of it, the y1 prime u1 prime plus u2 prime y2 prime. We can let, again, kind of similar idea, is we're going to let pieces equal something. And if I notice, if I let these two equal 0 and the other ones equal p of x, f of x, we end up actually getting a nice little system we can solve. And we can use a rule from systems called Cramer's rule. And Cramer's rule is where you can take a system and you can solve that system using determinants. And so you may not have ever seen Cramer's rule, but x is equal to, so the solution to xy is the solution, and the solution to x is where we take the coefficients of a, b, c, d, of the xy's in those, and we find the determinant of that. And then to find x's, you replace x's coefficients with the constants coefficients that are on the other side of the equation. So you'd have c, b, f, e, and we're going to find that determinant. And then you take a ratio of the determinant of your coefficients, determinant of this matrices that's created by replacing the constants with the coefficients of x, you'll get what x is. Same thing, y is the ratio of the determinant of where we took the coefficient matrix that we had, but we replaced the coefficients of y with those constants, CF. So A, C, F, D, F, and then A, B, D, E is your determinant of your coefficient matrix. That's Cramer's rule. And again, we're letting U1, Y1, U1 prime Y1 plus U2, Y2, U2 prime Y2 equals 0. And we're letting U1 prime Y1 prime plus U2 prime Y2 prime equal f of x. And so from this, we now have two systems and two equations and two unknowns to solve. So we can now use Cramer's rule. Cramer's rule is where we're going to have U1 prime is going to be, notice we have a U1 prime and a U1 prime, U2 prime, U2 prime. Those are my constants. Those are my variables you can think of it. The constants of U1 prime are Y1 and Y1 prime. The constants of U2 prime is U2 and U2, so Y2 and Y2 prime. And the coefficients, constants on the side are 0, f of x. So using Cramer's rule, U1 prime will be the coefficient matrix, so Y1, Y2, Y1 prime, Y2 prime. And then we replace the coefficients of Y1 prime with those constants. We'll do the same thing with U2 prime, and we can find both U1 prime and U2 prime. By the way, Y1, Y2, Y1 prime, Y2 prime, that's just the Wronskian. So we're just basically dividing by that Wronskian. This is one reason the Wronskian can't be 0, because then we'd be dividing by 0. So we find out that U1 prime is minus f of x times Y2 over the Wronskian, and U2 prime is Y1 f of x over the Wronskian. So this was a lot of work just to get down to these formulas. We now will use these formulas to solve these. So we're going to solve the differential equation y double prime plus y equals tangent of x. This one does not annihilate, so we can't use the annihilator method, so we must use the variation of parameters method. All right, so first thing we have to do is find out what y1 and y2 are. So the first thing you need to do is solve the homogeneous equation. The homogeneous equation is y double prime plus y equals 0. We then find the auxiliary equation, m squared plus 1 equals 0. So m equals plus or minus I. So my y sub c, my complementary solution is c1 cosine of x plus c2 sine of x. We can now find the Wronskian. So the Wronskian is going to be cosine x, sine x. The derivative of cosine x is minus sine x. The derivative of sine x is cosine x. So the Wronskian of that cosine x, sine x, if you want to put that in there, you can do that so you know what Wronskian you're doing here, is going to be cosine squared minus a negative sine squared. So cosine squared plus sine squared, which of course we know is 1. Okay, and now all I have to do is find out, to find y sub 2, is we have to find out, and I'm going to give it a name. We want to find out what this numerator is, this where we place the constants, the coefficients of the u1 prime with the constants 0 f of x, and then y2. So think of it as, we're going to call that, I don't know, we'll call it something, let's call it w1. We'll call the other one w2. So doing this w1, w1 is going to equal the determinant of, we're going to replace cosine negative sine with my 0 and f of x. My f of x is tangent of x. So I'm going to have 0 tangent of x. And then sine of x, cosine x. This is not a Wronskian because 0, the derivative of 0, of course, is not tangent of x. It's just, we're going to call it w. And I'm going to go ahead and find this. This is going to be 0 times cosine, which of course is 0, minus sine times tangent. So sine of x times tangent of x. So that's what w1 is equal to. w2 would be the exact same thing, where you take the cosine x and the minus sine x, and then the sine x, cosine x, and you replace the sine x, cosine x with the 0 tangent of x. And find this determinant. So you have cosine x times tangent x minus 0, and of course cosine times tangent is just sine x. Okay. So now we can go ahead and find out what u1 prime and u2 prime are. So remember, going back here to Cramer's rule, we're trying to find u1 prime and u2 prime. So u1 prime is w1 divided by that determinant, that the Wronskian, and u2 prime is w2 divided by the Wronskian. So u1 prime is going to equal w1, which we just found out to be minus sine x tangent x divided by the Wronskian, which is 1. All right. So this is equal to, just to make life a little bit easier here, this is equal to tangent is sine over cosine. So this is sine squared over cosine x, because sine times tangent is sine squared over cosine x. And then we need to find out what u1 is, not u1 prime. So we need to take the integral of that. You can use technology to do this. You can use u substitution to do this. I don't care how you do it. But you're going to find out that it's the natural log of the cosine of x over 1 minus the sine of x minus the sine of x. Okay. u2 prime is w2, which we found out be sine of x over the Wronskian of 1. So u2 prime is just sine x. So u2 is the integral of sine of x, which is negative cosine x. So now we're ready to find out what our particular solution is. Our y particular is u1 times y1 plus u2 times y2. u1 we just found was that natural log of the cosine x over 1 minus sine x minus sine x. y1 was cosine x. u2 we just found out was minus cosine x. y2 was sine x. So there's your y sub p. Your y sub p is the natural log of the cosine x over 1 minus sine x all times cosine x minus cosine x times sine x. So now we can get y. Y is your particular solution plus your complementary solution. Your complementary solution with c1 cosine x plus c2 sine x plus your particular solution, which was the natural log of the cosine x over 1 minus sine x minus sine x all times cosine x minus cosine x times sine x. And there's that particular solution. And this is all you do with this, is you have to find that complementary, that associated homogeneous equation, find your complementary solution, and then use that to find your Wronskian, and use that to then find using Cramer's rule.